Welcome to lecture 4 of the Machine Learning 1 course. In this lecture, we are going to talk about probability distributions. In the previous lectures, we have discussed a lot about probability, different types of probability. Then we have talked about especially Gaussian distribution, estimated the parameters of the Gaussian distribution. But is Gaussian distribution the only distribution that we fit? That's not true. I mean, we have seen different types of distributions, and what we discussed for this Gaussian distribution is the most common distribution. What we also saw was that we fit Gaussian distribution in regression problems, but does it fit everywhere? The answer is no. And in this lecture, what we are going to cover is some other famous probability distributions. So we are going to talk about probability distributions. Like we said, what the probability distribution is, a distribution that provides us probabilities of different possible outcomes of an experiment. So these probabilities correspond to different values of a chosen random variable. The random variable can be discrete, it can be continuous. And what we need to understand is first, what is density estimation? Let's say we have a lot of observations. What we want is we want to fit a distribution across this observation. We want to fit some probability distribution. It can be anything. So when we estimate this probability distribution from the observed data, that is referred to as density estimation. For example, in our previous module, we have seen that if we are given data and we are trying to fit a Gaussian distribution, then when we estimate the optimal choice of mu and sigma, then we are actually conducting density estimation for that case. Now, the challenge is that this is fundamentally, this estimation, density estimation, this is fundamentally ill-posed. If we are given data, there can be infinitely many distributions that can give the same observed data. There are two choices of distributions. The first one is parametric, the second one is non-parametric. As the name sounds, the based parametric distributions, these are model. So in these cases, the distributions have a well-defined shape. Then and there are some parameters that need to be tuned, and based on the choice of these parameters, the distribution adapts to the data. For example, the Gaussian distribution, it is controlled by the parameters mu and sigma square. And the way we fit this distribution is, for example, using maximum likelihood estimate or using maximum a posteriori estimate. Then there is another set of distributions called non-parametric. The difference here is that in this case, there are still some parameters, but they don't really change the form of the distribution. In the parametric case, the shape of the distribution is is already fixed, and there are only limited flexibilities that you can have in terms of tuning the distribution with certain parameters. But in the case of non-parametric, the shape of the distribution is not fixed. And there are still some parameters, but they are mainly used to control the model complexity, and the form of the distribution depends on the size of the data. If you have a very dense data, you might get a very different distribution compared to very sparse data. Now, since parametric distributions are very commonly used in these set of modules in this lecture, we are going to primarily focus on parametric distributions. So, for example, if we have discrete random variables, it is very common to use binomial distributions, so Bernoulli and beta distributions, or multinomial distributions. For continuous random variables, we use, for example, Gaussian distributions. One more important thing to understand here is what are conjugate priors. So if you recall this term, we discussed this term as well when we were discussing posterior distributions. If you have distribution, the posterior distribution with same functional form as the prior, then what happens is, we will see also in the later lectures, it becomes quite easy to conduct Bayesian analysis. So this combination of the prior and posterior distribution coming from the same functional form, this is referred to as conjugate priors.